All right, today we're going to talk about something really cool, one of the smartest ways your computer prevents total chaos. And, believe it or not, it works a lot like a post office. We're talking about mailboxes. You've been there, right? You're deep into your work and boom, the application just freezes up, or it crashes completely. Even worse, maybe you go to open a file and it's just a jumbled mess of garbage. It feels totally random, but I'm here to tell you a lot of the time it's not. So what's the culprit? Well, often it's two different parts of a program trying to talk over each other, grabbing for the same thing at the exact same time. Imagine two people trying to write on the same line of a whiteboard simultaneously. It's just a mess. So today, we're going to dive into this really clever OS Postal service that stops all that chaos from happening. Okay, but wait a second. Why do these processes need to cooperate at all? I mean, if they all just stayed in their own lane, we wouldn't have this problem, would we? Well, as it turns out, that cooperation is absolutely crucial. Yeah, it really boils down to three main things. First up, sharing info. You know, when you copy something from your web browser and paste it into a document, that's two separate programs working together. Then there's speed. You can take a huge, complicated task, break it into little pieces, and have a bunch of processes work on them all at once. Super important with today's multi-core CPUs. And finally, modularity. It's just smart software design to build things out of smaller, specialized parts that talk to each other. So, okay, processes have to talk. What's the most obvious way to make that happen? Well, you just give them a common space where they can both write things down, right? Let's think of it like a big shared whiteboard. The fancy term for this is shared memory. Basically, the OS carves out a little piece of computer memory and says, hey, you two processes, you can both use this spot. And it's super fast, right? It's direct. Seems simple enough. Any process can just mosey on up to this whiteboard, read what's on it, or scribble a new message for someone else. A classic example of this in action is something called the producer-consumer problem. So, picture this. One process, the producer, is creating some data. Let's say it's a compiler making assembly code. And then you have another process, the consumer, that takes that code and does something with it, like turn it into machine code. They use a shared buffer, that's our whiteboard, for the handoff. The producer drops off the code, the consumer picks it up. But here's where it gets messy. What happens if the producer tries to write a new line of code at the exact same instant the consumer tries to update its status on the board? Uh-oh, they're both trying to write to the same place at the same time. That collision, my friends, is called a race condition. And the result? Total chaos. The data gets corrupted. It's like one person is writing hello while someone else is trying to erase that exact spot. You just get gibberish. In software, this is what causes those weird, impossible-to-reproduce bugs and system crashes. This is exactly the kind of thing that could make one bad browser tab take down your entire browser. So this really brings us to two main ways for processes to communicate. You've got shared memory, our fast but really chaotic public whiteboard. And with that method, it's all on the programmer to make sure nobody crashes into each other. But then there's another way, message passing. And this is like our organized postal service, where the OS itself is the mediator, the postmaster, making sure everything happens in a nice, orderly line. And at the heart of this postal service model is something called a mailbox. So let's check out how this simple idea creates a much, much safer system. Now, the most important thing to get about message passing is this. The processes can talk and get in sync without sharing any memory. There is no common whiteboard. They're totally separate, living in their own little worlds. So if they're isolated, how do they talk? Well, they use a mailbox, which is also sometimes called a port. And this isn't a shared space they can both scribble on. Nope, it's a special object that is completely managed by the operating system. Think of it like an official government-run P.O. box. And how it works is actually pretty elegant. Let's say process A has some data to send. It doesn't just dump it in a shared area. Instead, it wraps it up in a message and tells the OS, hey, send this to mailbox M. The OS kernel, our friendly postmaster, takes the message and sticks it in the mailbox. Then, whenever process B is ready, it just tells the OS, hey, got anything for me in mailbox M? And the OS hands over the message. Simple as that. All right, so this is the big moment. How does this simple little postal service completely get rid of that nasty race condition we were worried about? The secret sauce here is synchronization. And the way it works is through something called blocking. See, unlike the shared whiteboard where processes can just run around like crazy, here the OS can actually step in and say, whoa there, hold on, you need to wait your turn. So here's what that means.
With what's called a blocking send, the process that sends a message is basically paused. It just stops and waits until the other process actually receives it. And on the flip side, a blocking receive means the receiving process will just sit there and wait if there are no messages for it. This perfectly timed handoff is called a rendezvous, and it makes sure that everything happens one at a time in the right order. So the key takeaway is this. Because the OS is the gatekeeper, it is literally impossible for our producer and consumer to get in each other's way. The producer sends, then it has to wait. The consumer tries to receive, and if nothing's there, it has to wait. There's no way for them to collide. The race condition isn't just avoided, it's solved by the very design of the system.
Okay, so if this message passing thing is so much safer, why would anyone ever use that chaotic, shared memory approach? Well, like pretty much everything else in computer science, it all comes down to a trade-off. Look, shared memory is blazingly fast. Once that shared space is set up, the processes can zip back and forth without having to get the OS involved every single time. But, and this is a big but, it's up to the programmer to handle all the safety stuff to prevent those race conditions. And let me tell you, that is really, really hard to get right. Message passing is slower, no doubt, because every single message has to go through the OS. But the payoff is huge. You get all that safety and synchronization for free. And really, that's the whole story. When you use the OS Postal Service, this message passing with mailboxes, you're trading a little bit of raw speed, but what you get back is a massive gain in safety. And, just as importantly, simplicity for the people writing the code. So that leaves us with the big question every software architect has to face. When you're building something and you need different parts to talk to each other, what's more important to you? Is it the raw, untamed speed of that shared whiteboard? Or is it the rock-solid, built-in safety of the Postal Service? The answer to that question can determine whether your whole system is stable or a ticking time bomb.